Okay, we're now going on to refraction video number 5, which is entitled The Visible Spectrum. And what you've got there on the screen is probably one of the most iconic album covers ever produced by a band. And it's Pink Floyd, it's Dark Side of the Moon. One of the tracks is Shine On You Crazy Diamond, and we were doing diamonds last time, but it's really iconic. I've actually got this as a vinyl, if anybody remembers what vinyl looks like. Big black things that you put on a turntable. First released in 1973. Pink Floyd started in late 60s sometime. So this is an album cover before CDs, and certainly before streaming, before people even had or even thought of mobile phones and smartphones, and albums came as big square things 12 inches across. So pretty famous. Just thought I'd bung that one in. But what we're going to do is have a look at the physics of this sort of thing and have a look. And we're going to do this, as I have done in the rest of these videos, I'm going to do it via the medium of some calculations and some worked examples. So what we've got here is we've got a beam of white light, and the beam of white light comes in to the prism. The colouring here isn't quite right, because as soon as the beam of light enters the prism, it starts getting split up into its components of the visible spectrum, which you can see here, Roy-Gabiv from the top going down. I mentioned this quite a bit earlier on, a couple of times in some of the earlier videos. So really this isn't quite right for physics purposes. We should have some red here and then the different colors coming down here for violet. Okay, so I've redrawn that, and here's one I produced earlier. And it's a simplified version. I've got white light coming in here and it's split, and you get the complete spectrum of visible light coming down here, red down to violet. So I'm going to keep coming back to this and referring to this. I'm going to add some further information. It might be an idea for you actually to pause the video and draw this. You don't have to do it in colors, but some of the, in fact, quite a bit of this lesson is going to revolve around this particular diagram. So you might want to pause the video and draw it and label red at the top, violet at the bottom, and we've got the entire spectrum of Roy-Gabiv down here, which I can just about fit in there. The entire spectrum. We don't just get red and violet, we get the entire visible spectrum down the right hand side there. Spot my writing now. Violet. So a good idea to be able to copy that down. We've got the normal line, we've got our white light coming in there, and as always with most of these, we would measure the angle here, and I'm going to put that as 50 degrees, and that is not the angle we're going to do any calculations with, because that's not theta 1. Theta 1 is in fact this angle in here. And so straight away you can work out that theta 1 is equal to 90, take away 50, which is equal to 40 degrees. And we're going to use our Snell's law formula. We're going to work out some different angles. We're going to work out what is the angle theta 2 for the red light, and theta 2 is this angle here for red. Just working out where to put that. And theta 2 for violet is this angle here Okay. So the implication of this is because as soon as white light made up of all the different colors superimposed upon each other, and you can't see them separately when you look at light from the sun, for instance, as soon as the light enters the prism, red is refracted the least and violet is refracted the most. In other words, if I was to draw the line that goes straight on, I'm not going to spoil this diagram. If I was to draw the line that goes straight on across there, you can see how far away the rays of light are refracted. Red refracted the least, violet refracted the most, but theta 2 for red is the largest, theta 2 for violet is the smaller angle, because remember, we're always measuring the angles from the normal. So violet refracted the most because it's bent the most away from the straight line if the prism wasn't there. So violet comes all the way down here and has the biggest amount of refraction, and red light has a lesser amount of refraction, but the angles theta 2 for red and theta 2 to violet are reversed in their size, if you like. Theta 2 small for violet, theta 2 is large for red. Now, the implication of that is that different colors have different refractive indices, and that is actually the case because red light, the refractive index for red light, now remember this is a glass prism, and roughly speaking the refractive index for light, I've been talking about this number, which is about 1.5 for glass. It's air outside, it's a glass prism. But the numbers are very slightly different from 1.5 depending on the color, because the colors get refracted by a different amount. So the refractive index for red light is in fact about 1.51. It's not far away from 1.5. And the refractive index for violet light, N, is equal to 1.53. Now remember, the bigger the refractive index, the more the light is refracted away from its original path. Right, now typical exam question here, which would be broken down into different parts, is that we'd need to find theta 1. Well, we've done that already. Theta 1 there, we've worked out for all the light, all in one white beam, is 40 degrees. We want to find out the angle for theta 2 using this refractive index and this angle. We want to find the angle theta 2 for violet using this refractive index for and theta 2 and that value of theta 1. And then finally, I would like to work out what the angle, it's called the dispersion angle. I'd like to find out what this angle is in the middle here, just there. It's called the dispersion angle, and it's basically the difference between theta 2 for red and theta 2 for violet. And this could be some sort of typical exam question that involves prisms and light being split up into excuse me, into its various colors of the visible spectrum. So we're going to work through this. I will keep plonking this back down here, but I'm just going to take it off for now. So I've given you an idea of where we're going. We're going to work out theta 2. Well, first of all, I've already done that bit about theta 1, sorry. I've already worked out what theta 1 is, the correct angle between the normal and the ray of light. I'm just going to transfer that information. Theta 1 is equal to 40 degrees. And I've got the refractive indices for red, 1.51, for red light, and I've got 1.53 for violet light. Just off there, I've just taken them across. Okay. So the second bit is, that's part A. So the second bit is I want to find theta 2 for red light using the information that I've got. Okay, so it's Snell's law. It's n equals sine theta 1 over sine theta 2. You should be getting quite good at doing this sort of thing by now. And I can put the numbers in, and for red light, n is 1.51. I've got 1.51 equals sine of theta 1, 40 degrees, divided by sine of theta 2 for the red light. If you want, you could put some little subscripts in here so you know what you're talking about. And we could say that it's theta 2 for the red light, and I'll just put an R in there. So I'm going to work that out. What do I do? Put sine theta 2 for red up there. For red is equal to sine of 40 degrees divided by 1.51. You then work that out, and that comes out to be 0.426. So I can get theta 2 is the inverse sine of 0.426, and that comes out to be 25.2 degrees. Then I can do exactly the same thing and find theta 2 for the violet light. So I can replace all of this information, and I could do violet, and it wouldn't be 1.51 there, it would be 1.53. And so I can change all of this, and I can go all the way through, and I can find out that I'm just going to skip some of this, and I'm going to say, I'm just going to go to that bit, and I'm going to do 1.53 is sine 40 over sine theta 2 for violet. I can rewrite that and get sine theta 2 for the violet light is sine of 40 over 1.53. I can do the inverse sine bit. Theta 2 is the inverse sine of whatever that is, and that comes out to be, if I do that, I'm just checking my notes because I've worked all this out already. It's a little bit different from 0.426. It's 0.420, and you can check all of this if you want. You ought to get into the hang of actually using the sine button and the inverse sine button and using your calculator to get the right answer. And so theta 2 comes out to be 24.8 degrees. So I can go back to my original diagram, and I can see that theta 2 here is 24.8 for violet, and it's 25.2 for the red. It's a slightly bigger angle, 25.2 there, 24.8 there, and the dispersion angle is just simply take the angle for violet, which is smaller, away from the angle for red, which is bigger, and I shall do that on the next bit, remembering 25.2. Just going to transfer the information up here, is that theta 2 for these two for red is 25.2 and degrees, and for violet is 24.8. So I can get rid of that. And just go back to here. So what is the dispersion angle, or the angle between the two beams of light inside the glass? So the dispersion angle is the bigger angle for red, which is 25.2. Take away the smaller angle for violet, minus 24.8 degrees, and that obviously works out to be 0.4 degrees. And that would be a major part of any sort of block test question, if they exist. I haven't even looked at the block test questions yet, or I've seen this in previous exam questions. Right, what else can we do? We can move on from that, getting a little bit more complicated, as if that wasn't bad enough. We could actually start to look at what are the angles when the beams of light come out over here. And I could add on some more stuff here. I can put on a normal line for red. I could put a normal line on for violet. But that's getting a little bit too complicated looking at white light. So what I'm going to do is I'm going to quickly redraw this, and I'm going to change this into just one type of colored light. Put that there. And it's one type of light, and it's what's called monochromatic light. Monochromatic just means one color. Let's carefully get rid of that. And I can have what this is called monochromatic light. Now, because it's one color only, I'm not even going to be able to fit this in, look. Monochromatic light, that means light of one color. So because it's light of one color, it can't be split up into any more colors because it's only one color to start with. Put in my normal, and so it's going to come, whatever color it is, it's going to come over here. Can't be split up anymore because it's only one color, and then it's going to come down here, something like that. Okay, and I haven't said what color it is yet. Now, I mentioned this before. This is an equilateral triangle, and all the angles inside an equilateral triangle add up to 60 degrees. So that 60 down there, 60 down there, and 60 up here. Okay, I've got my beam of monochromatic light where θ1, once again, that's 50. So θ1 can be 40. We'll just keep it simple and keep it at 40 degrees. Okay. Now what I need to do is I'm going to find out the some angles, not necessarily here. I want to find out some angles over here this time so I can see how far the whole beam of light gets bent over there. And one of the things I can do is find out the refractive index. I'm going to give you another piece of information because you won't be able to do this otherwise. I'm going to say that θ2 in here is 26 degrees. So I've got θ2. I know that it's 26 degrees in there. If we went back to our previous example, this looks a little bit like the red light. And the red light, if I remember rightly, the red light came out at 25.2. When we did this and we calculated θ2, it was 25.2. So this is a little bit more deeper red than just ordinary red. At 25.2, it's 26 degrees. That angle there is slightly bigger. So it's bordering on infrared, this beam of light here. It's a very dark red color as it comes out of there. Okay, so I've told you that θ1 is 40, θ2 is 26. I'm going to get rid of the whole thing and just put θ2 there. I'm going to write up here, θ2 is 26 degrees. for theta 1 is 40. And the first question is I want to work out the refractive index of this glass, and we know that it's going to be roughly 1.5. So you can think ahead, and if you don't get these answers quite right, like if you had 6.8 for instance as a stupid answer, you'd know it wasn't right, because you know the answer is going to be roughly 1.5 for the refractive index. And again, I suggest you pause and you draw this information as a separate diagram, because this is going to be a separate example. We've already done the first bit. We found that theta 1 is 40 by taking 50 away from 90. I'm giving you theta 2 is 26 degrees. So pause the video and copy this diagram down neatly into your jotter. Or if it's not a jotter, it must be lined paper or something, whatever you're going to do. So lined paper probably. The way I did this actually was I did this nice and big, made that 12 centimeters. You might just be able to see a little mark there, and that's at 6 centimeters. And I know that that's got to be 12 and that's got to be 12, but I just made the apex, I made it directly up above the midpoint there. And then when I drew those lines, they came out to be about 12 each, which is fine. So 12, 12, 12 gives you 60 degrees, 60 degrees, 60 degrees. It's an equilateral triangle where every side is the same length. Okay, so we're going to move on, and we're going to find the refractive index. So part A, find n, the refractive index. And Snell's law again. This is just using the same stuff again and again and again, but we're just applying it in different situations. So I've got n is sine theta 1 over sine theta 2. I don't know what n is. I know that theta 1 on the outside is 40. And I know that theta 2 on the inside is 26, because you're given that information. So if you divide sine of 40 by sine of 26, just going ahead in my notes, so I don't have to put it all into my calculator, I get 1.47 is the refractive index for that prism. And we already talked about, I talked about it earlier, because that angle 26 was bigger than the red light that we did in the previous question, where the refractive index was 1.51. This has got to be slightly lower. So it's got a refractive index of 1.47. So that's the first bit that I want to look at. Right, the second bit is I want to work out, I'm going to put in a normal line on here now, and you can go back and add in your normal line, which is at 90 degrees here. And what I want to calculate is this angle here. I'm just going to call it angle D, okay, because I can't think of a different letter to use. I want to calculate that angle D as the beam of light comes out. Now, in any calculation, you're always using an angle between the ray of light and the normal, and the ray of light and the normal. So if I do any calculations, I'm going to find the angle between the ray of light and the normal. So I'm going to calculate that angle, and then I know a bit of geometry, that is 90 degrees. So this angle here, I'm going to call that angle C, and that angle C is one that's going to come out in my calculation. Okay, so we're going to work through this. We're going to use this information that the angles in the triangle are 60 degrees each. I'm just going to take a brief pause here. I'm going to stop the recording, and then I'm going to come straight back in. So although this is lesson 5, I'm going to make this video 5A, which will be a bit shorter than normal, and then I'll come back and we'll work out how to do this. So I'm just going to give you some time. I'm going to take some time as well. I'm just going to stop this recording right now and come back and finish it